Okay, so we're going to take a look at conic sections for a little bit. The first one I wanted to highlight today is the parabola. So this is not the parabola that you have learned in previous classes. It ultimately is the same, but it's a much more formal way of looking at it. So let's go ahead and take a look over here at this. So one thing to remember is that all conic sections are able to be described by this formula right here. And just by switching around different values of A and B, we can create the various shapes. So if A and B are in fact the same, we always get a circle. If in fact they're different, if A and B are different and their product is positive, that's kind of interesting. If A times B is actually above 0 and they're different, that actually is what makes an ellipse. And that's not how I normally define it, but this is the more thorough way of saying it. So if they're both positive or both negative, that's going to make their product above 0. That makes an ellipse. Now, as it turns out, if the product is negative, it makes a hyperbola. And of course, the only way that can happen is the product would be negative if one is positive and one's negative. And last, if their product is in fact 0, then one of them must be 0. That makes a circle. Makes a parabola. Now, it is important to note that that's not both of them 0, just one. Now, as it turns out, if you take something from this format right here and work with it, you can always tweak it into being one of two forms. And this is a little bit hard to understand as to exactly why that's the case. We'll go over that in class and I'll try to flesh that out. But this is going to describe a parabola that either opens up if P right here is positive, or one that opens down if P in fact is negative. So this is one version, and that would be the case if the y squared part, if the B value is 0. So A is still there, but B is gone, that's going to produce this case. But if B is there and A is gone, then it's going to produce this. And it turns out we always do the same thing. So notice that Y and K go together, X and H go together. And so we end up with a side-to-side parabola. So again, it's going to open up this way if P is positive, and it's going to open up to the left if P is negative. So one example that I have of that right here is a simple parabola right here. I wrote the equation down here so we could see it. I just typed this directly into Desmos, and it turns out this is the vertex. There's my H, and K is 2, 3. Just a nice easy one. So 2, 3 is right here. That's going to be my vertex. And the value, if this 8 is for P, then that makes P equal to 2. And this is known as our focal length. And the focal length is actually quite important because it actually tells me that the distance from that vertex up to that focus is exactly 2 units. So that's why I put the spot up here exactly 2 units away from the vertex. So it's coordinate 2, 5. And for that same reason, the directrix, which is this guy down here, is going to be exactly 2 units behind that focus. What can I do? Yes, you can. So that's going to be our directrix, which is y equals 1. Now, as it turns out, the definition of this is a strange definition. It's that all of these points, every single time you pick a point on that parabola, it has to be the same distance from this focus as it is from this directrix. So I have a little compass right here to try that. So I'm going to actually measure how far this point is to the directrix down here. So looks like around there. Now, this is not perfect. I'm not trying to be perfect. I'm just trying to give it an idea. There's the distance, and if I slide it up here, you'll notice that that's exactly the same distance there. If we picked another point over here, this distance right here to the directrix is right there. See if I can get it to hover where I wanted it, right there. If I slide it over, you'll notice, again, that distance is exactly the same. And every single one of these points has that same thing in common. And sometimes it's nice to put some notation on that, but other times, you know, it might make the diagram look a little bit messy. But this is what makes the definition of a parabola what it is that sometimes, however I do that, those distances always have to be a constant. So in terms of laying out the notes, here's kind of how this plays out. So my goal was to get through maybe the first couple of these, and then I will take it from there. So this is a problem where it's a y squared, so it's going to open left or right. And since it's positive, it's definitely going to open to the right. That means that my vertex is going to be at negative 4, 3. I'm going to come over here and go negative 1, 2, 3, 4, 1, 2, 3. Right there, there's my vertex. Now, because this 12 right here is for P, and that makes P 3. So since it opens to the right and my vertex is right here, I want to move 3 units over, 1, 2, 3, in the direction it opens. That's going to be my focus. That's negative 1, 3. Again, I just moved over 3. And again, if I move backwards 3, 1, 2, 3, I'm going to get a vertical line at negative 7. I just moved backwards 3. And that's the building blocks of my parabola as I go through this thing. Now, this distance, again, that was P, which in this case was 3. And then we go that way, P as well. Now, this is a little strange. Again, this is called the focal width, length. The focal width, as it turns out, is the number 12, that thing right there. And we're going to do half of that length up and half of that length down. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And it turns out this creates almost like a little box. And the back of the box is the directrix. The front of the box has the focus on it. The middle of the box has the vertex. And all of these points, it just kind of goes like this and goes right through the edge of the box. And that's a really nice way to make a formal value. And so this distance right here from here to here, let's see, I think I'll do it in blue. That distance right there is the distance 12. And unfortunately, this is actually known as the Latus Rectum, but that's just what they call it. Now over here, you'll notice that I have an x squared. So it's going to either open up or down, but I want to put it in the right format. So x minus 1 squared is supposed to be a 4 times something. So if I factored out, actually, as it turns out, a negative 4, that's going to be a y and a minus 3 halves. So it looks to me like my vertex is going to get 1 comma 3 halves. So this 1 comma 1.5 right in here. There it is. Now this one is actually going to open down because as it turns out if 4p is negative 4, that makes p negative 1. So that means I'm actually going to move down 1 unit right here to get to my focus. I'm going to go up 1 unit to get to my directrix. They're always perpendicular to each other. So this is the line, I guess it's y equals 5 halves because this was 3 halves, 4 halves, 5 halves. And then again, like we said, this is kind of got to be a little bit careful because the width isn't negative, but the width is 4. So I'm going to go over 2. Oh, I just realized I had that in the wrong spot. There should be here. This paper counts by halves. So I'm going to have a width of 4. So I'm going to go over 1, 2 from the focus. I'm going to go back 1, 2. This again is my box that we refer to. And then all I have to do is kind of just try to do a decent looking curve, plane connect the dots. I've got my directrix on the back of the box, the focus on the bottom, the vertex in the middle, and 2 points that actually make it on the curve. And that kind of gives us a little bit of a feel for how those things behave. So I think I'm going to stop that video right there, and I'll put the rest of those. I don't know that I'm going to bother to do number 3, 2, and 4 on this video. I'm going to jump back and we'll look at the back side of this worksheet where we're in standard form for the next one. All right. Have a good day. Bye.